Hi ladies and gentlemen, in the last video we have seen full subtractor. Now these full subtractors are not the way we subtract numbers. Instead we use the 2's complementing method or 1's complementing method. So in this video I tell you about a 4-bit subtractor circuit with the 2's complementing method. So it basically relies on a 4-bit adders and complementing circuit. So let me start with that presentation. So the speech is organized into your learning outcomes, then a 4-bit subtraction using a 2's complementing method and the circuit for that, and we will see the simulation in QUCS. Then the 4-bit subtractor can be made with integrated circuits like a 7483, how that is done, what is a wiring diagram for that. Then the same thing, the 4-bit subtractor can be made in verilog, both the device as well as the test bench. Then the summary of your understanding. So what you will learn in this video is that you will learn the 2's complement method of subtraction of two 4-bit numbers. Then you will learn to implement the 4-bit subtractor in QUCS and verilog. Then you will appreciate the wiring diagram for full for 4-bit subtractor with the integrated circuit is 4-bit subtractor. Then if you look into a 4-bit subtraction, say let us look at these numbers A and B. Let us look at 4-bit numbers A and B, which may be A3, A2, A1, A0 and B3, B2, B1, B0. Now let us compute the difference between A and B, say A minus B. Suppose let this A be 100, that is 8, and B is 1100. So it is 8 minus 12, that should be minus 4. The result should be minus 4. So how I do that in with the adder circuit is that first I take the 2's complement of the number B. So what is the 2's complement of the number B? It is a 1's complement of that number plus 1. So what is a 1's complement of 1100? It is 0011. Just to invert these bits, so it is 0011. Plus 1, it makes a 0100. So this 0100 is the 2's complement of 1100. I take the complement and add 1 to that. Complement is 0011. Add 1 to that, it becomes 0100. Now I add this 2's complement with my original number A. So it becomes a 1000 plus 0100. So this is 0011. So the number is 1100. The sum is a 1100. So here what I do is first I take the number A, take the 2's complement of the number B, then I use a 4-bit adder to make a sum. And here if you see that the carry is a 0, this 0 carry indicates that the number is a negative number. So the sign of this number is the inverse of that carry, inverted value or the inverted value of this carry. So the sign is the inversion of this carry, and if this carry is a 0, then that means the resultant sum should be 2's complemented. Okay. If this carry is a 0, then the 0 carry indicates that the result is negative. In such a case, the last result, that the first sum should be 2's complemented. So I have to take the sign bit as 1. So I have to invert this carry and keep it as a sign bit, and I have to invert this one and add 1 to this. So I have to take the 2's complement of this. Though 1's complement of this is 0011, and the 2's complement becomes a add 1 to that, it becomes a 0100. So the carry is inverted to form the sign bit. So this together with the sign bit and this number, it is 10100, which is minus 4, as that is the correct result. Now that is a case without any carry. Now what is a case without consider the case with a carry. So what happens here is, suppose I have consider the case with the carry. So here I have, say, the bit pattern A, that is 1000, and it is a 0011. That is 8 minus 3. It must be a 5. The result should be a positive 5. So what I do is I take the 2's complement of 0011. It becomes 1100 plus 1, that is 1101. So add to this 100. A is here 1000. This is the 2's complement of B, 1101. I add to that, it becomes 1 0 1, 1 plus 1 is 1 0. So here you have a carry. In that case, if the carry is a 1, it indicates that this number is a positive number, the difference is a positive number, and nothing is to be done to this 0 1 0 0. This carry is inverted to form the sign bit, which is a 1, it becomes a 0. So the number is 0 0 1 0 1. Okay, which is plus 5. The carry of 1 indicates a positive result. This is inverted to form the sign bit. In this case, nothing is to be done to the last result. So a circuit based on this argument is shown in this figure. So what happens is this is a 4-bit subtractor circuit. What happens here is here, if you can see what is in the circuit, are two 4-bit adders are there. Two 4-bit adders like a 7483 or any 4-bit adder is here. So the number A comes here and this number B comes here. This number B is complemented by 4 inverters. Okay, then the Cin of the first 4-bit adder, that is connected to 1. So together with this addition of this 1 and this complementing, it becomes a 2's complementing circuit. It becomes a 2's complementing circuit. This number B is inverted and 1 is added to that. It makes gives you the 2's complement of B. This 2's complement of B is added with the number A, and here I get the sum S3 S2 S1 S0. And we have to be very careful about this carry. If this carry is a 0, then it means that the number is negative, and this S3 S2 S1 S0 must be 2's complemented. So if Cout is a 1, is a 0, this is inverted here to make this point a 1. This is my sign bit, that's a 1. And here this is used to control an inverter setup. This is a inverter with a XOR. If this point is a 1, then whatever comes here as 3, S2, S1, S0, that will be complemented here, and that will be added here. This high here will add a 1 here to this Cin, so that what I ultimately get is the 2's complement of S3, S2, S1, S0. Okay, this other, so this is connected to a second 4-bit adder. Here the other bit A1, A3, A2, the other value of this A that is kept at a logic 0. So whenever the Cout is a 0, what happens is 1's complement of S3, S2, S1, S0 is taken here, and 1 is added here to make it a 2's complement. So ultimately what is done here is a 2's complement of this intermediate sum that appears here along with the sign bit, which is a 1 now. Okay. Now, what if this Cout is a 1? In that case, I don't have to perform any further 2's complement. So if Cout is a 1 here, that means sign is a 0, or it's a positive number. So if this is a 1, this inversion, it becomes a 0. So the sign bit is a 0, Cin is a 0. And here this S3, S2, S1, S0 are not complemented, so they just appear as such here. 0 is added to this, here Cin is a 0, so this S3, S2, S1, S0 appears as such here at this point along with the sign bit. So that's a positive result. So this is how a 4-bit subtractor circuit works with the 4-bit adders. Now I can implement, I can simulate the circuit in QUCS. So I will go to that. So in this QUCS, I can take this, I can realize this circuit. You can see here, first there's a 4-bit adder to which I apply one input A, that is, this is A3, A2, A1, A0, and these are my B3, B2, B1, B0. They are complemented here. Okay, and the carry in is connected to 1, so this carry in together with these 4 inverters, that makes a 2's complementing setup for B. Now these bits, these 2's complement of B and A are added with this, and the sum is taken out, and mark out this carry here. This 12th pin is a carry, so that is inverted here, and here 4 inverters, 4 XOR gates are used to make a controlled inverter. If this carry bit is a 0, then this thing is 2's complemented. Here this is your carry in, and this is a sign bit. This inverted value comes here. This is my sign bit, and this is a second 4-bit subtractor to which one input A that is connected to a logic 0. This is connected to logic 0. If this controlling bit, if this C intermediate, if this is a low, then 2's complement is taken. If this is a 1, then this point is a 0, and no complementing is needed. This sum appears as such at the output. Okay, So these are my output D3, D2, D1, D0, and this is sign bit. Now I can perform the simulation, and you can see here these are A3, A2, A1, A0. This is the second number B3, B2, B1, B0, and this is sign bit, and this is the difference bits. Here you can see that this number is 0, 0, 1, 0, that is 2. This number is 0, those 2 minus 0, sign is a 0, and the difference is a 0, 0, 1, 0, that's a 2. Or if you come to this line, say it's a 0, 0, 1, 0, that is 2, minus 0, 1, 1, 0, that is 6, so the result should be a minus 4. So the sign bit is a 1, and the result is 0, 1, 0, 0, that's a difference is a 0, 1, 0, 0, that is a minus 4. Or take any other possibility, say suppose here 1, 0, 0, 0, that is 8, minus 0, 0, 1, 1, that is 8, minus 3, that's a 5, that's a 0, 0, 1, 0, 1, that is a plus 5. And here it is a 1, 0, 0, that is 8 minus 1, 0, 0, 1, that is 9. 8 minus 9, it should be a minus 1. So the sign is a 1 and the difference is 0, 0, 0, 1. Or you can take any other pattern that way and appreciate that. Now let me go back to my presentation. Now this is how I implement the circuit using 7483s ICs. So when you go to the lab, you can take two 7483 ICs, an inverter and a XOR gate, and you can implement this circuit. This is the first 4-bit adder to which I apply A values, and B values are applied through a complementing circuit. Okay. B values are applied through a complementing circuit. The C in of this is kept at high, that makes it a 2's complementing circuit. Now there is a C out coming here. This is my C4, this is my C out. C out is inverted here. Okay, this is taken to this inverter, and this is inverter, and this comes this is a sign bit. Okay, sign bit, and this is used to control this 4-bit controlled inverter circuit using 7486, and that sum is applied to the 7483. Okay, the others input of that A value of that is connected to all bits, are 4 bits are connected to logic 0. Then the difference comes here. These are D3, D2, D1, D0. 4 LEDs are connected here in normally on state, and this is connected to the sign bit. Okay, so then you can apply suitable patterns for A and B here, and you can see the difference here, the D3, D2, D1, D0, and the sign bit. And once we are happy with this, you can implement this full 4-bit subtractor in it's a 4-bit subtractor in a verilog and other thing. I will show you this code in here. This is a 4-bit subtractor. Now this is what I have to. I will need 2 things in this verilog module for. This is a verilog module. In this verilog module for 4-bit adder, I have to 4-bit subtractor. I need 2 things. One is I need a 4-bit adder. This I made in one of the previous sessions. I made a 4-bit adder .v in one of the previous sessions. Then I need a 1's complementing circuit. So this 1's complementing circuit is for taking the 1's complement of the second number b. So that appears like this, something like this. This is a module 1's complement. Output wire is a 4-bit X bar. This input wire is a 4-bit X. Okay, then this is I use a gate level design, and I am realizing that not array as such, like X bar 0 is X0 complement. This is a NOT gate, say N1. X bar 0 is X0 complement, and X bar 1 is X1 complement. X bar 2 is X2 complement, and X bar 3 is X3 complement. Okay, then IN module. So what it takes is, if X is given to this module, X bar comes out, 4-bit X bar comes out. So this I use in here. I'm just following that circuit. I'm realizing that circuit at the gate level. So this 1's complementing circuit is 1's complementing module is used, included, then 4-bit adder is included. Now what happens is I start a module say 4-bit subtractor, some name. Then output wire, this is a difference, and output wire C out, or this is actually the sign bit. Even though I call it the C out, this is a sign bit. and then input is a 4-bit X, 4-bit Y, and input wire Cin. Cin is kept at logic 1. Now there are some internal nets wire sum1, this is output of the first 4-bit adder, then complemented value of Y, then X, that is 0 0 0 0. This is the other input to the second 4-bit adder. Then some intermediate value. We will see that here. I have this intermediate value. This is then wires are there, C0, C1. So this Cin is kept at 1. The first carry in, that is kept at 1. This is to facilitate. I am using 1's complement circuit, or this 1 along with this carry in 1, that makes it a 2's complementing circuit. So first I take the 1's complement of Y. This is the second number. This is complemented. So this comb is just a Y complement. That is the 1's complement of Y. So then 1's complement of Y is added with X along with Cin, which is a 1, to form intermediate sum 1 and C0. If the C0 is a 0, then I have to take the 2's complement of this sum 1. If the C0 is a 0, I don't have to do anything. If the C0 is a 1, I don't have to do anything to this sum 1. So then I realized this inverter, this CO is C0 is inverted to make a C out. This is my sign bit. Okay, even though I call it a C out, it's actually my sign bit. Now I use 4 XOR gates to make a controlled inverter here. If the C out is a 0, this inter 0 is same as sum 1 0. If C out is a 1, then this inter 0 is a complement of sum 1 0. Likewise, inter 1, inter 2, inter 3 are made. This is the output of my controlled inverter. Now I assign X equal to 4-bit pattern 0 0 0 0. This is the other input to the second full adder, second 4-bit adder. Now I invoke another 4-bit adder here, adder 2, 4-bit adder of adder 2. What is the input to this 4-bit adder? One input is my this capital X, which is nothing but 0 0 0 0. Okay, then this intermediate sum inter. Okay, this is a controlled output. Either it is a complement or 1's complement of sum 1, or it is the same as sum 1 inter. Then this C out determines if C out is a 1, then 2's complement is taken. If C out is a 0, nothing is done to sum 1. Now what is the output? I get this diff and C out C1. C1 has no significance for me. I am interested in this diff and this C out, which is a sign. Now N module. Now I can make a test bench for this by invoking this function here. I include a 4-bit sub.v. This 4-bit subtractor is added here. Then a module is written test bench. X and Y are input, they are register. Cin is also a register. This difference and C out are wires. Then I invoke this 4-bit subtractor with some name y1 difference carry out. I say carry out. This is actually my sign, and x y Cin. This so an instance of this 4-bit sub is made. Now then the other things are the same as in the previous test benches. Here I apply some patterns here. Cin is kept at 1, and some bit patterns are applied here, x for x and y, and we finish this. Now I can run this simulation here. So first I run this 4-bit sub. It is compiled without any error. Now I run this test bench 4-bit sub tb.v minus o a.out. Now I have to run this a.out. Now you can see that initially these are all in an indeterminate state. Here x equal to 0, x is 0 0 0 0, y is 0 0 0 0, difference is 0 0 0, and the sign is 0. This carry out is actually the sign. Then 1 0 0 0 minus 0, the sign is a 0 and the difference is 1 0 0 0. Here x is 1 1 0 0 and y is 1 0 0 1, so this is 12 and this is 9, so the difference should be 3 with a positive 3. So the sign is 0 and difference is 0 0 1 1. Now it is 1100 minus 1101. This should be a minus 1. So the sign is a 1 and the difference is 0001. And x is 1111 and y is 1101. Okay, so the difference should be positive 2. So carry this sign is 0 and the difference is 0010. So it is positive 2. X is 1000 and y is 1100. So the difference should be minus 4. So this is 10, this is 8 and this is 12, so the difference should be minus 4. So the sign is a 1, this is 0100, that is a 4, that's a minus 4. So this is how I realize a 4-bit subtractor in Verilog. Now let me go back to my presentation. So now coming to the end, what you understand in this video is that you understood the 2's complement subtraction. You saw the case with and without carry. So if there is no carry, then I have to take the 2's complement of the first sum. If there is a carry, then I don't have to do anything to the initial sum. So you learned the 4-bit subtractor circuit and implemented it in QUCS and Verilog. Then you understood the wiring diagram of a 4-bit subtractor using the 7483 chip and other ICs. So that is the end of this presentation. I thank you all.